Welcome eNet 130, Bellingham Technical College's Semiconductors course in the Electronics Engineering Technology program. This lecture is dedicated to Zener regulation of our diode rectified AC signals. This is a follow-on to our discussion of full wave rectification in our previous lecture, in which we discussed both center tap and bridge rectifier styles and the advantages of a full wave rectifier in that it didn't throw away one half of your input waveform. So you basically ended up getting double the frequency in your output, you retained the whole waveform, and from the standpoint of getting true DC rather than pulse DC, you made it easier to correct for that ripple. So if you were using a capacitor, for instance, in your output circuit here to smooth between the points and continue your voltage signal at a closer to a true time invariant set DC, by putting those peaks closer together with full wave rectification, you made your job easier. We're going to discuss in this lecture very quickly one of the limits on using a smoothing capacitor to get true DC rather than, or something closer to true DC rather than pulsed, and then bring forward the idea of a Zener diode to further regulate the voltage output of our smoothed rectified DC to give us an additional level of control in what is getting now closer to a true time invariant DC. So we're going to have diodes to rectify, and then we're going to bring forward the idea of a Zener diode to smooth, we'll have a capacitor to smooth, and then we'll use the Zener to make that smooth signal average value not so susceptible to our load. So figure 3.22 here in our Fiore textbook basically shows the type of configuration of our Zener regulator. We'll have a current limiting resistor, of course, and of course, reverse biased Zener diode in parallel with our load. And that is going to be positioned in our rectifier circuit here immediately after our capacitor. So we've got in this case, we have a bridge rectifier. So we have our pulse DC coming out of the diode bridge. We have our smoothing capacitor, and we're going to discuss in this lecture some of the limits of that smoothing capacitor. And now we're going to introduce this limiting resistor and Zener diode as an additional level of signal conditioning before we get to our load. So to do that, we're going to use TINA, and we're going here to a TINA circuit. We're going to use a center tapped rectifier in this case. This is still full wave, but from the standpoint of TINA, the center tap makes it a little bit easier to deal with our transient signal analysis because we can ground it. We don't want to be adding grounds in our bridge rectifier because we can effectively cut part of our circuit out. So for this exercise, I'm using a center tapped, which would work just fine in practice. So I have my current limiting resistor hooked up right now in preparation to add my Zener later, just for ease of use in our lecture discussion. And it's very small, it's only 1 ohm. And my load resistor now, the load, which would be, of course, a whole nother circuit that I'm powering with this DC power supply, my load is 100 ohms. So that's considered, a moderately light load. Remember that the bigger the load resistor, the lower the current that flows through it, so the lighter the load. So 100 ohms, fairly high impedance external circuit I'm powering, so it's a light load. I have my Zener ready to go in the correct position, but first I'm going to take a look at the transient output without it and kind of make the case for why it's necessary. So I have a 2 millifarad smoothing capacitor here and a 100 ohm load, and for now my 1 ohm current limiting resistor isn't gonna play a big part. So I do my transient analysis. I'm going to look at maybe 3 waveform periods, and I'm not plotting all of the things I could be plotting coming out of my rectifier like we did in previous discussions. I'm just going to take a look at just that output D versus ground. So this is the voltage signal that the load sees. So this is what we care about. This is what our circuit that we're powering with this DC power supply sees. So it's seeing something on the average of, we can measure it. We're going to set our measurement bar to right about the midpoint of our ripple, and we have about 10.8, 10.9 volts is our average value, and some amount of ripple, not too bad. Okay, now suppose somebody comes along and says, boy, I want a lot more current in my circuit, and they hook up a 20 ohm load. So that's going to draw a lot more current. So let's see what happens to our average value. We know our ripple is going to increase because we just dropped the time constant of this RC circuit. But let's see what happens to our average output value, because that's probably what we're counting on to deliver an average power. So we're going to run our transient analysis again, and that's going to update our graph. We'll get a little warning because our Zener is not hooked up. And immediately we saw, as expected, the ripple increased, our variation, but let's see what happened to the average value. So we're going to set our measurement tool midway through the ripple, and we just dropped 1 volt out of 10. So by changing our load without realizing, we didn't change the setting on our power supply. We thought we were delivering 10.8, 10.9 volts, and somebody hooked up a different circuit, and all of a sudden we're only delivering 9.8. So if it's our lab buddy, they're saying, hey, wait a minute, did you set the power supply correctly? And you'll say yes for a higher input impedance circuit. So it would be nice to have a power supply that didn't vary with the amount of current, where its voltage output, its average output, excuse me, didn't vary with the amount of current we wanted to draw with the circuit we're powering with it. Now that gets pretty annoying when we have a power supply from which we want a certain average voltage. So one of the ways that we can take care of that is to use a property of a Zener diode, which is the fact that it has that very, very stable reverse breakdown voltage. And it's designed to work in the reverse breakdown mode. So if we connect our Zener across the circuit here and take a look at this node up at the top, we know that whatever the reverse breakdown voltage is that the Zener is rated for, that Zener will open and conduct with negligible resistance once that voltage is exceeded at that point. So if we were willing to sacrifice some output voltage at our load, or just increase our secondary transformer output to compensate, and we were willing to live with whatever the Zener breakdown voltage is at our load, we would never have that big shift when we switch the current demand of the external circuit, because we're always going to get the Zener breakdown voltage. That's effectively, we've pinned this point at that value. Now it could be less if for some reason we weren't getting that, our capacitor wasn't able to supply it because our transformer secondary wasn't high enough, and this output slumped too much. But if we can control that with the proper size capacitor, and we've got our secondary transformer output set right, we can make sure that we don't get that shifting average every time we change the load. So let's go ahead and set our load back to its original value and kind of track this one through. So let's see what our Zener is set up to give us. We can double click on the Zener, and look, we've got properties that Tina is modeling that are intended to simulate a commercially available Zener, the 1N2804. If we click on the 3 buttons, we can check out its reverse breakdown voltage, BV breakdown voltage. So this Zener has a 6.8 volt reverse breakdown voltage. So as long as this node here is 6.8 volts or greater, the Zener will conduct current such that anything past that sees nothing more than 6.8, or nominally so. There's certainly some variation. So we've got 100 ohm load, and we have our 6.8 Zener voltage regulator plugged in, so let's run another analysis and see how that changes things. We're going to assume that our external circuit is okay with just 6.8 volts, knowing that we could always adjust that. So we're going to run it again, and we've seen the waveforms changed a little, and most important, our y-axis value changed to 7.15. So we'll use our measurement tool again, and let's get about the midpoint, so because we're comparing average to average. So now check it out. Our average output is right at the Zener breakdown, 6.84, give or take. So the Zener's doing what we think it should be. It is regulating the voltage output at the load. We introduced a little bit more ripple because we have another path for current to follow. The Zener is not perfect. It does have some inherent resistance in it. It isn't just a switch. But for the most part, we're getting the output we would expect based on the breakdown voltage. So here's the proof of the pudding. Let's ask for more current in our external circuit. Let's change that R load back down to 20 ohms, and by reducing that R load value, reducing the impedance effectively of that external circuit we're simulating with it, we're asking our power supply to give us more current. So let's see how this average value changes when we run the model again with a higher current draw, a higher load in the output circuit. So we'll run our transient analysis again, and ooh, nothing really seemed to happen. Our y-axis is at about the same place, our waveform hasn't changed, and we can use our measurement tool again, hit the midpoint, and depending on exactly where we put it, we are within measurement error of the 6.8. We also know that we have more current flowing through this whole part of the circuit. So chances are we're dropping a bit more voltage over the Zener from its internal resistance, but nominally the same. Without the Zener regulation, we were losing 10% of our original output voltage. Now, negligible change. Didn't do much for our ripple, unfortunately. There are other things that will take care of that, but in terms of our average voltage output, by including our Zener, we made our average voltage output of our power supply circuit current draw or load independent. So that's the magic of adding this extra component to our DC power supply. So we'll just take a moment right here to step back through all the things that we're doing to give ourselves that nice DC with only a little ripple. Looking at the different stages of our power supply. So we've got a certain periodic, we'll call it sinusoidal, it's probably coming from the grid. So we have some kind of sinusoidal voltage signal coming in maybe from the wall. We use a transformer to adjust its level, but it's still positive, negative, periodic sinusoidal signal. We have our rectifying diodes that give us pulse DC that take that negative going signal and basically flip it up. So we have our double the frequency full wave pulsed DC. We got a smoothing capacitor that continues to give us a voltage signal even when that pulse drops when we roll down off of our peaks. And now we have a Zener that, in exchange for some reduction in the potential that we were getting from our capacitor, for some small sacrifice in that, we are now getting that smooth DC that won't vary when we draw different amounts of current. So we have several stages that are all working together to give us some nice smooth DC. So hopefully you all can appreciate everything that your power supply and your electronics trainer, if you're using one for your labs, or any other kind of DC power supply does for you. There's quite a few parts and circuit components necessary to turn that time varying signal coming in from your grid power into something that is approximating as much as possible the output of a battery. So that is it for this quick mini lecture on Zener regulation for multi-load power supplies. And so we'll continue with other ways we can use diodes to regulate voltage signals in the next lecture.